attend the doubt clearing session. So keep in mind, till now we have been discussing negative feedback, where we were trying to make sure that our system is stable. If my negative feedback becomes positive feedback, which happens when the denominator becomes equal to 0, it actually becomes positive feedback. So the signal starts adding up in phase. Okay, instead of being in out of phase, it starts adding up in phase and starts growing. That is called positive feedback. Now we know that the feedback, when I want an oscillation, I want maximum amount of feedback, so we remove the beta network completely. So that's what is written here. Oscillation may occur at any beta though. However, you know that oscillation may occur better as beta tends to 1, because as beta reduces, my phase margin increases. And if my phase margin increases, my system is going to be more and more stable. So if my so therefore in an oscillator, whenever we are designing an oscillator, we want to make sure that my beta is close to 1, and therefore we actually connect the output and the input back. Okay. Now we have already seen that the Barkhausen criteria is that it is equal to 1 and 180 degree. Okay. In the previous one, we had written minus 180 degree because all our systems had poles which give you negative phase shift, but whether it is 180 or minus 180, it will still give you the same. Denominator will tend to 0.
Sir?
Yes.
So in that case, what should we call the feedback, like the feedback circuit? Would it be negative feedback circuit?
It will be positive feedback. So when your Barkhausen criteria of oscillation is satisfied, then we call it as positive feedback or regenerative feedback.
So just before that, like just before it reaches 180 degree, the amplifier, like that, while the amplifier is amplifying, so before that it would be called negative feedback.
No, not like that. See, when you build an oscillator, you are building it to oscillate at a particular frequency. Okay, you can design oscillators in different ways. One of the ways is you can put purposefully positive feedback. Okay, in another case, you can put negative feedback, and at one particular frequency, that negative feedback becomes positive feedback. That means the Barkhausen criteria is getting satisfied at that frequency. To give you an example, if I have an LC tank, okay, and if I initially charge this capacitor to a certain voltage, and then suppose I have an LC tank like this, and I have charged this to a certain voltage, then I suddenly close this switch at time t equal to 0, right? Then what happens? The stored electrostatic charge will get converted to magnetic energy. So it will start building up current in this magnetic energy. Then after that, the magnetic energy will again get there will be energy exchange between the two things. Okay, so there is no positive feedback at this point. This one is, I don't know what happened. Okay, so this one, what happened? Okay, so here it is just that the pole of the system, natural response, has infinite response at square root of LC, 1 by square root of omega equal to, which is the oscillation frequency. Okay, here it is energy exchange. So there are oscillators that can be built differently. Okay, well, of course these both have to be ideal, but in reality these two are never ideal, so then the oscillations tend to die out. Now in order to make sure that they don't die out, what do? You put a negative resistance, and the negative resistance is realized using positive feedback. So I won't discuss the effect, incorporation of negative resistance in this course. We'll just discuss a phase shift oscillator because it comes in the context of negative feedback, which satisfies this Barkhausen criteria of oscillation. Okay.
So the same circuit can be used as a negative feedback for at other frequencies.
Yes. 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 But keep in mind, if your phase margin is not there, at other frequencies you apply, you'll get something, but what will be dominant is that frequency where it is oscillating, where you do not even give an input. So it is an oscillator to be for all practical purposes. You got my point, right? See, at that particular frequency it will oscillate. if your phase margin is not there. So that means whether you have negative feedback at other frequencies or not doesn't matter, because it is giving an output which is undesired, which you do not want. Okay, so it becomes an oscillator at that point, at that frequency. By the way, oscillator is a very interesting area, nice math. It has a lot of nice differential equation based analysis. Coupled oscillators are even more interesting. Okay, you can look up videos on injection locking, on how mechanical things, how mechanical oscillators lock, and based on that people have built electrical oscillators, how they lock. So very interesting things. Richard Feynman has explained those very beautifully. I don't think anybody on earth can equalize his way of explaining things. Please listen to his lectures. Okay, so now various views of feedback system. So what we have seen is that if I have built a system, I want to build an oscillator now at a particular frequency. So what will I do? I will put negative feedback. Okay, this is a meaning of negative feedback. If there is a plus here and a minus here, means negative feedback. But at one particular frequency, the forward path gives you 180 degrees of phase shift. And of course, there is another 180 degree of phase shift. So the total phase shift in the loop is 360 degrees. You can have somebody will say, you know what, I won't do this. I will build a system which gives, I'll put positive connection here, and I'll give a 360 degree phase shift at that particular frequency. That is also fine. It's up to you how you realize it. Another person will say, you know what, I won't even give 360, I'll give a 0 degree and 360 degrees are almost the same. You cannot distinguish. How will you distinguish in real world whether there is a 0 degree or 360 degree phase shift? How will you distinguish? If I am seeing it on the oscilloscope, can I distinguish? Anybody? So your eyes won't be able to distinguish 0 degree and 360 degree. But if I transmit a sine wave of audio frequency, let us say, okay, and I give a 0 degree and 360 degree, I'll hear the 360 degree later than the 0 degree phase shift. Okay, the same frequency will be heard later. So that is what 0 degree, 360 degree would mean. So so you can try the oscillator using any of these things. The above mentioned phase shifts are happening at the oscillation frequency omega naught. Not at every frequency, keep in mind, not at every frequency do you get a 180 degree. It is impossible to get that. Similarly, not at every frequency will you get a 360 degree. Neither will you get a 0 degree phase shift for every. Only at one particular frequency, if you get that phase shift here and you make the connection in an appropriate manner here, you will get an oscillation at that frequency. Okay. Now the ring oscillator, we have already looked at it. During when I was doing my PhD, this was a very nice question. So I'll pose the question like this. Okay. So let's first go through this, and the way the question was posed during my Viva, during PhD Viva, was like this. And it's a qualifier exam where you are asked questions by 10 faculty and you have to go to each individual faculty. One of the faculty asked this interesting question. I'll discuss that later. Now, if I have a single stage common source amplifier and I connect the output back to the input, okay, there is only one pole here. Okay. For oscillation to occur, we need DC phase shift of 180 degrees. So now this to this is a phase shift by connection, 180 degree phase shift. But from here to here, I need a DC phase shift of 180 degree. A DC 180 degree, that is negative feedback. Frequency dependent phase shift of 180 degrees. So we need a, sorry, I made a mistake. DC phase shift is this, sorry, my bad. So we need a, this is a DC phase shift. This is a DC phase shift. Okay, this is a DC phase shift of 180 degree, DC phase shift of 0 degree, DC phase shift of 0 degree. Okay, and a frequency dependent phase shift is over here. This is a frequency dependent phase shift. Now, for the for the common source, so what we need is, for oscillation to occur, we need a DC phase shift of 180 degree, that is negative feedback, which we have. But frequency dependent phase shift of 180 degree is also required, which we do not have here, because from here to here, if I look at the frequency response, the output will be, this connection is giving me 180 degree, but otherwise the output will give me 90 minus 90 degrees of phase shift at infinite frequency. Okay, it will give me minus 90 degrees of phase shift at infinite frequency. Okay, so the maximum frequency dependent phase shift that the single stage common source amplifier gives is 90 degree at infinite frequency, implying no oscillation. How about a two-stage common source amplifier? Okay, the ideal inverse signal. So here there is no here to here. We have to give a DC phase shift, which is realized using this. This realizes a DC phase shift of 180 degrees, and these two together give us 180 degrees of phase shift at infinite frequency. That means for all practical purposes, I will never get an oscillation. I will get an oscillation at infinite frequency, which I cannot measure. Okay, so this, therefore, a two-stage ring oscillator would not oscillate.
So can you explain this again?
So this thing is a DC phase shift. Am I clear? There is no doubt here, right?
The DC 180 degree phase shift.
DC phase shift of 180 degree, right?
Okay.
That means I now, from here to here, I need a frequency dependent 180 degree phase shift, correct?
Yes.
But why, this is a two-pole system. What is the maximum phase that it can phase shift that it can give? 180 degrees,
180
right?
degrees.
At infinite frequency. So this will oscillate at infinite frequency, which I cannot measure anyway. So for me, this is as good as not an oscillator, right?
Yes.
Because I cannot measure it.
Ideal component.
Okay.
So what is the ideal component that you have added?
Just that is for mathematical purpose.
Okay.
That is just for mathematical purpose to give you a ideal subtraction. 180 degree phase shift. Okay. Now let's look at the three-stage common source amplifier. We already analyzed this in the previous class. So here we can say that each stage has a pole at omega naught. So it is a three-stage. Each stage is giving a gain of A naught. A naught is equal to minus GM times RD. Now this connection itself gives a DC phase shift of 180 degrees. And we need a frequency dependent phase shift at one particular frequency where it is going to be 180 degrees, so that the total phase shift in the loop is 360 degrees. So that means at omega oscillation, the phase shift is 180 degrees. That is, each stage gives a phase shift of 60 degrees. Thus, tan inverse of omega oscillation divided by omega naught equal to 60 degree, because each stage is giving a phase shift of tan inverse of omega divided by omega naught. So therefore it is going to be 60 degree. Omega oscillation, we already derived this. The oscillation frequency is equal to √3 omega naught. The minimum DC gain A naught required is given by A naught greater than equal to 2. That we have also derived earlier. If the loop gain equal to 1 is sufficient for oscillation if omega at omega oscillation, why do we say that loop gain should be greater than 1? In order to make sure oscillation is sustained as temperature, voltage and process change, we have to make sure that we satisfy this, because if we do not, if the loop gain drops to less than 1 because of any of these changes, temperature, voltage or the process, which we call it as PVT change, then I'm not going to get an oscillator. Remember, gain is a function of temperature, voltage and process. So which I have already explained, isn't GM PVT dependent, because GM is a function of, there is mu n C ox. Okay, so mu n C ox, mu n is mobility. Okay, C ox, oxide capacitance, is dependent on oxide capacitance is also dependent on how thick and how the polishing and all the fabrication happens. So all these things come into the picture. So therefore, we have to make sure that our loop gain is greater than 1. So this part we have already done. We know that a 3-stage can give us an oscillation. Okay. So I will skip this because I want to directly get into the phase shift oscillator. I'll skip the resonant oscillators for now because, okay. Now, this is the CR phase shift oscillator. I'm going to make a creative problem on oscillator, so make sure that you understand the concept. Okay, the CR phase shift oscillator. So this is a C capacitive resistive network. Okay, the above is a CR phase shift oscillator which incorporates a phase shifting network. So CR is going to give you a phase shift. Okay. In order to analyze the above circuit, we break the loop and find the loop gain as follows. Okay, so we are putting a minus K gain here. This is an ideal block. We'll replace that with a real block. Okay, so what we'll do is we break the loop over here. We break the loop over here, and then we apply an input voltage and measure the output over here. Okay, now applying KVL in the first loop, so we can apply KVL here, KVL here, and KVL here. So the loop equations can be written like this. So I1 times R. So keep in mind the current flowing through R is I1 minus I2. So that's why I1 minus I2R. I times the impedance of the capacitor equal to V in. So that is this first loop. Second loop is here I2 minus I1. The current flowing is I2 minus I1. Yes, I2 minus I1 times R. And here it is I2 minus I3 times R, and there is I2 times SC. So based on that, this is the second loop equation. And then finally, the third loop equation is given by this expression. Oh, sorry, is given by this expression. Now, V out equal to minus K times I3R, because V out is nothing but this voltage is equal to I3R, this voltage times this. Now keep in mind there is a negative sign. This voltage is I3 times R. Okay, I3 is flowing this way. This voltage is I3 times R. I3 times R times minus K equal to V out, and that is what is written here. Okay, minus I3 times R times V out. Therefore, the loop gain equal to A beta equal to V out by V in is given by this expression where alpha equal to this, and we can solve it, which alpha equal to this. So this is the overall alpha. Okay. Now the loop gain A beta, keep in mind, feedback gain AF equal to A divided by 1 plus A beta. Now 1 is dimensionless, less and real. A beta has also to be dimensionless, also should be dimensionless. Okay, dimensionless, and should be real. Otherwise it cannot be, this becomes an imaginary quantity. Okay, so can you please work it out? Please solve these three equations. So please write this equation down, this equation, and the third equation. Please write that down. And V out equal to this, A beta equal to this. Please write it down in this manner, where alpha equal to 1 by omega RC. Please write that down. I'll wait for 2-3 minutes. Once you have done, please raise your hand.
So I couldn't understand why it should be real.
Because, 1 second. Process means how the transistor is getting fabricated. Somebody has a question, what is process? Yeah, process means when the transistor is being fabricated, the doping and all concentration change, and that changes the characteristic of the transistor, the ID sat and all those things. Okay, why alpha, why A beta should be real, right? Am I right?
So yes.
Okay, because this gain of our amplifier, can it be imaginary? If it's a something, what does the imaginary thing mean? It means it's going to give a phase shift or something, right? Correct. So the overall thing here, 1 plus A beta, the denominator here, this is a real quantity. So this thing has to be real. So I don't know how to put it, but
So when we write A of j omega, then there is some imaginary part there, right? So why can't AF be imaginary too?
uh, okay, I'll come up with a better explanation. Okay, I owe that explanation. I'll give that. Okay. So I have to find out a better way of putting why should it be dimension, why should it be.
Sir, if A beta is real, then it is actually giving a 360-degree or a 0-degree phase shift, which corresponds to a positive feedback. But for any other case, can it be happen that it is giving a negative feedback? So maybe that's why.
Oh, no. Now I understand. What does the okay, sorry, I got lost. Okay, now I have this answer. So look at it this way. What does the Barkhausen criteria say? That this should be what? 0. Correct? Yes or no?
So yes.
When will this be 0? Only if A beta is real, right?
So yes, now understood. I thought that that was a general statement.
No, sorry. I now do you understand, all of you? When will this be 0? Denominator to satisfy the Barkhausen criteria of oscillation is only when this is real. If it is not real, if it is imaginary, then you end up with, you cannot ever have this term as 0. There will be a
The
phase shift.
Barkhausen criteria is A beta greater than 1. How it
Barkhausen criteria is, no, that's what I said. Barkhausen criteria is A beta should be equal to 1 and angle A beta equal to 180-degree at omega naught.
Oh, okay.
We make this A beta greater than 1 to make sure that it oscillates even when there is temperature, voltage and all the variations, because it will eventually come back to 1 at a particular frequency. And that's where it is going to oscillate. Okay. So, so now since the loop gain is a real quantity, why do we have it as a real quantity? To satisfy Barkhausen criteria. That is this. Okay. So that this denominator becomes 0. Denominator of AF tends to 0. Okay. So please work this out and prove that the oscillation frequency will be given like this. Is that clear? Just like in the okay, let's finish. At this frequency, the loop gain should be greater than or equal to 1. We make this greater than or equal to 1 so that it is robust in case of this thing. So we make A beta. So you can find out, you ignore this quantity k by 1 minus alpha squared, 5 alpha square, and alpha can be obtained root 6. You plug in that value, it will turn out to be this thing. So k should be greater than 29. Which is the gain of k. Now k can be realized using this op-amp topology. That means RF by RI should be 29. So RF should be 29 times bigger than RI. Therefore, the overall circuit can be, the first CR network is here, the second CR network is here, and the third CR network is realized with this. But you might say, why is this resistance not connected to ground? The resistor is connected to virtual ground because of the op-amp action. So in reality, this is what you will do, and this ratio to this ratio will be equal to 20, should be
29.
greater than 29. Okay, and this is a phase shift oscillator. I think I finished 1 hour before schedule. If any further doubts, I don't want to go any further. This should be sufficient for your exam. Now,